Hi class. When we left off on our notes the other day regarding the atmosphere, we talked about how scientists decided where the layers of the atmosphere would be divided. And we discussed that the major factor to their splitting of the atmosphere into 4 layers was the temperature. And just to recap, a little reminder, the temperature scientists found through collecting data does drop. It gets colder in the troposphere. But they decided to call the next layer the stratosphere because they noticed that something in the stratosphere was making the temperature slightly rise or stay a little steady in that layer. As they went further up in collecting data, they noticed that in the mesosphere, which they named the mesosphere, made that layer get colder as you went up in elevation. And lastly, the thermosphere, the particles got warmer and warmer and warmer as the space between the particles gets colder. And so with this information, they came up with the areas of the 4 layers and named them. Today we're going to talk about another main difference in the layers of the atmosphere. It is called air pressure. The definition of pressure is important for you to understand. It's a continuous force exerted on an object by something that comes in contact with it. So when we're talking about air pressure, we're talking about molecules in the air, the gases, the liquids, and the solids that are creating force on other objects in the atmosphere. Those other objects could be other molecules, or it could be something else. How much pressure does the atmosphere create on us? Well, because gravity is pulling those air molecules towards Earth, every square centimeter, which is about the area of the tip of your finger, is being pressed down with about 2 pounds of weight. So if your mom or you have a 2-pound weight at home, imagine that sitting on your fingertip, okay, all the time. But if you don't have that size weight, another way you can think about it is like a huge can of like baked beans or some kind of hefty soup sitting on your finger. And that's how much weight is pressing down on just that little area. So if you think about how much is pressing down on our head and on our shoulders, pressing down on us, it's quite a bit of weight. So why don't we feel this weight? Well, what we need to understand is that air actually is moving in all directions because we know that air has a lot of thermal energy. That's what allows it to be in gas form. And so those particles are moving around pretty fast in all directions. And so not only is the air pressing down on us due to gravity, but it's also pushing in on us as well and up on us. Now I'm going to do a demo to kind of show you a little bit more about what I was just discussing with air pressure. Now what I have here is just a jar with some water in it. And what I'm going to do is place an index card over top of it. And I'm going to flip this over. What do you think is going to happen? Take a minute to record in your notebook what the setup looks like. Draw a picture briefly, describe what each object is, and then kind of make a prediction about what you think is going to happen. Alright, we're going to move on now, and I'm going to show you what happens, and then help you explain how this works. Did you think that was going to happen? Well, let's talk about why that happened. When I flipped this over, the water moved to the top part of the glass because gravity was now pulling the water down that way. Since the glass was upside down, it was near the opening of the cup. But it didn't go past that. Why not? Because air pressure was also pushing up on this note card. So even though gravity was pulling the water down, air pressure is also pushing up on the note card in the water. And so they were balanced forces, and that way the water did not go downward. Let's do this again one more time. You don't have to change your drawing, but you might find this interesting. Here is a lid with lots of tiny holes in it. We're going to do the same demonstration. So right now, I'm going to put the lid on the cup, and I'm going to dump this over. We're going to observe what happens. You saw that some water comes out as I'm flipping it, but right now I think you can see that there is more water, and it only comes out when I tilt it back and forth. We're going to talk about why this happened later, but I want you to think about it. Okay, so let's get back to discussing the 3 factors that affect air pressure. So air pressure isn't always the consistent thing. Sometimes we have high air pressure, sometimes we have low air pressure, and sometimes we just have air pressure that's pretty consistent in the middle. The 3 factors that change the amount of air pressure in a given area of the atmosphere: water vapor, elevation, and temperature. Notice that it spells out the word wet, so we can make that acronym WET: water vapor, elevation, temperature. And since all 3 of those factors are constantly changing in the atmosphere, so does air pressure. More specifically about water vapor. As the water vapor molecules increase, air pressure decreases. So it's a negative correlation. As there's more water vapor in the air, which just means that water from the surface of the earth has evaporated into the air, when there's more of that in the air pressure does the opposite, it decreases. And that's called a negative correlation. Now, why does the air pressure decrease when there's more water vapor in the air? This is because you can think of water vapor as a beach ball. A water vapor molecule being a beach ball. And a regular gas molecule in the air being a bowling ball. Let's pretend both of those are the same size, so they take up the same amount of space. But if you think about it, pressure is about creating force. Which one of those create more force on something? A beach ball or a bowling ball? And I think we all can say the bowling ball would create more force because it has more mass to it. So since water vapor doesn't have a whole lot of mass to it, it creates less density in the air, which then lowers how much pressure the air molecules can make. Alright, so elevation is the second factor. As elevation or altitude increases, air pressure decreases. What kind of correlation is that again? Negative. And that just means that they're opposite of each other. As one goes up, the other one goes down. So why does this happen? Well, as we go further up in the atmosphere, remember how we talked about the thermosphere has fewer particles in it. So if there's less particles in it, then they can't create as much pressure on each other or on other objects. Also, the farther you go up in the atmosphere, the less air molecules are above you to pull down on you. So as we go up, there's less and less air pressure because not as much is being pulled down on top of you. Here's a diagram that kind of better explains that. We have this guy at the bottom of the mountain, right here, and then we have him up at the top. And over here is a column just kind of showing you the air particles in the atmosphere. And you can tell there's a whole lot more particles closer to the bottom, which is called higher air pressure. And then there are fewer particles at the top, which creates lower pressure. And so when he is standing at the bottom of the mountain, he has more of these molecules around him and also being pulled down on him. So he has a higher pressure on him. But if he climbs to that top of the mountain, it will be the opposite. The last factor, temperature. Temperature, as it increases, air pressure decreases. Again, a negative correlation. So when temperature increases, that means the air particles are moving faster and faster and faster. And they're also spreading apart. So if the same amount of particles are spreading apart, then that creates less pressure within a certain area. Because basically there's less molecules in that area since they spread further apart to create that pressure upon the particles. Now, the only place in the universe where there is no pressure is in a vacuum. And I'm not talking about a vacuum cleaner. A vacuum is a space entirely devoid of matter, so it has no air pressure. So it is a place where there is no gas, liquid, or solid, nothing. And we're going to simulate a vacuum in here, and you can volunteer to be part of the vacuum to see what might feel like, where there is no matter or very little matter. So that means that on Earth and in the atmosphere, there is at least a little bit of pressure everywhere, because there are air molecules, including liquids, solids, and gases in the air. The layer that has the most overall pressure would be the troposphere, the one on the bottom closest to Earth's surface. And this is because it is the densest and is located under all those other particles. And so they are being pulled down to Earth, and all the particles around it are pressing on each other. Now, what happens if you have two areas of varying air pressures near each other? An area of high pressure rushes toward an area of lower pressure until a balance of air pressure occurs. So basically, what does this cause? It causes wind. So around us in the troposphere, we often have varying areas of air pressure. Some might be higher because maybe the temperature is lower, maybe you're at a lower elevation, and maybe there are not very many water vapor molecules in the air, and so that would be an area of high pressure. And with that being said, there might be an area near it that has lower pressure. Maybe it's a little bit higher elevation and it's warmer air and it has more water vapor in it. And therefore, the air molecules in the higher pressure, we're going to rush to the area of low pressure until there's a balance of air particles in both of those areas. And that's when the wind will stop. So anyway, we're going to be moving into wind next week. And this is kind of a glimpse of what we're going to be talking about.